Hello everyone. In this video, I'm going to discuss the introduction motion of a falling body. And the idea I'm using here, the textbook, for a purpose to kind of develop a skill of going into a textbook or a book in general, going to a library and searching for a book about certain subject and trying to read that textbook. It could be a math or another scientific or engineering type of book. Uh, we're used to looking at videos, but videos don't necessarily address all the details or may not go into the theory, or it takes sometimes too long just to look at a bunch of different videos and not finding really what you're looking for. The books are always kind of the answer to this. So it's good to time either look at a textbook or find another book and try to go through it and see how it is structured and how they carry the steps. So as you see here, for this kind of introduction, uh, when the object is falling, uh, it's going to be assumed that two forces are acting on it. And we know that based on Newton's second law, that the force is going to be the mass times acceleration. And then there is some drag or some resistance um, due to the air. And you can see that they are opposite directions. So sometimes you will see this when G is used. Um, uh, Often, this is the notation negative mg because this is falling this direction and the y-axis is positive, and that's how was discussed in section 1.1 or previous video. But sometimes it is convenient to use kind of the velocity in a positive way, but based on that convenience doesn't mean everything is going to follow positive. Everything has to fall in place in the way it works. Like here, if you decide that something is positive, if something is it's in opposite, is going to be negative. Um, but it's okay. Here it's going to work out. You'll see. So here, there's Newton's law. You have the mass times the acceleration, which is the first derivative of velocity with time, and equals to the total force that is acting on it. Of course, the books will try to go into a detailed explanation to understand what's going on, and like this is one of the facts that on the Earth's surface, the force due to gravity is just the weight, and it is of course directed downward, and a lot of more details. What is the air resistance that I mentioned? Here, it's going to be described as BV. So if you have an object falling, and if we put mg this way, then if we represent this this resistance um, with some uh, coefficient there or some number that has to do with this resistance, it's going to be negative b times the velocity v. Okay, and b here is a positive constant that depends on the density and the air and the shape of the object. And hopefully, if we have time in the future, we're going to talk not about just things falling, but also things taking off, and explain that max Q thing that you hear when the rocket lifts off. um, at some point reaches max U and max Q, and the engines ready to throttle down. So what happens there? All right, so that's another subject, but just to give you the idea, it's connecting here with B, depending on the density and the air and the shape of the object. So applying the Newton's law, we obtain that this first order uh, equation, this first ODE, which says that the mass times the acceleration equals to the mass times the gravity minus some resistance. And to solve this, we're going to do separation of variables. And just to show you in next page, but I think here probably need to scroll down a little bit. Yeah, and show you this step before we go into separation of variables. Okay, so separation of variables, we see here that we have dv and we have dt, so it means you need dv on one side and dt on the other side. So what happens if I multiply by, I have m over dt, so I don't want dt to be with dv, so I need to multiply by dt, and we have m. So let's say we're going to multiply this by the other way, dt over m. Okay, so that's going to give us m dt over m times dv dt equal to mg minus bv times dt over m. All right. And as you see, that's the goal. And here we just end up with dv equal mg minus bv dt over m. And as you see, this has a v and this has a v. So let's divide both sides by mg minus bv, mg minus bv. And that's going to give you this step here. Okay. All right. Once you can pause the video or write it down. Then I think here it's not going to work with, I'll try, but probably it's not going to work. Um, yeah. So now let's just clean this up. Okay. So here is a sketch that kind of details the idea. And now we're going to integrate the two parts. Okay. So here, integrate these two sides. All right. So since you have an idea now about separation of variables, you can try it. All right, so it looks like you have in the denominator, so this is here 1 over mg minus bv. So you know the antiderivative is going to be natural log of this, right? Natural log of that. And because we don't know about the sign yet, we're going to put the absolute value for it because the domain of natural log function is positive inputs. And because v, just like 2x, you know, 1/2 x or something like that, so you need to divide by b or negative b. Okay, so that's gives us the left side, and the right side is just you have kind of 1 over m dt, right? So that's just going to be t over m. And we have a constant on the left and the right. Here plus C1, here plus C2 of them, right? Because if you do that, you're gonna have C2 minus C1, something when you bring the constants together, let's say to the right side, and you can just call this C, just like the previous videos. All right. So now, after the integration here, as you see this separation of variables require integration. So kind of to review. All right. So now, what is the next step between this 3 and here? That means we need to solve this equation, and which means let's multiply by negative b both sides. Multiply by negative b both sides. That's going to give you natural log of the absolute value of mg minus bv equal t times negative b over m plus negative b times c. All right. Then that means to solve this, we're going to take the natural log to both sides. And when we take a natural log to both sides, we should get this idea because e and the natural log are inverse of each other's. That's going to cancel, and that's going to give you the absolute value of mg minus bv. And here you'll have the 2. You'll have e to this, right? So you'll have e to this. Since we have addition, it means for the exponents, it came from multiplication. And just like the previous video, so you'll get this form. One thing here that we need to know, of course, in general, because this is a falling object, even though it's explained in a way, of course, for this object to fall, this gonna run to be a positive, and you have a constant A. What is the constant A here? The constant A is this e to negative bc, but also, even if you're not sure what you're going to do with the absolute value, you can say, I'm going to put an absolute a new constant there that's going to have the same sign as this, right? But of course, here we're going to look into mg to be bigger than bv for this thing to keep falling. But here also another explanation that A is replaces, of course, this other constant and having the same sign as this. Which means here you can drop this absolute value. Okay. Once you do that, it's getting V, of course, is not a problem. It's just kind of algebra, where you can bring this here to this side and bring this here. Okay. And that gives you this one after you divide, of course, by B. All right, so you'd have B. Let's go to that here. You'll have V equals to mg divided by B minus this thing here. All right. So what I want to show you here, this is what's called the general solution to the differential equation, and it's interesting, and you'll see it more often. Um, Here, to go a little more kind of the physics or the mechanics, let's turn this into an initial value problem and understand what's going on. For initial value problem, we're going to put this initial condition that v at t equals 0 is going to be some initial velocity. All right. So what happens here when you do that? Um, let's see. So here, when you try to use that initial condition, you're going to get v0 equal mg b minus a over b, and t is 0, right? So this is 1. Okay, so here is a nice trick. Usually you would kind of solve, then you find out you want to leave it one way. Look at what happens here. You see this v, this minus a over b here, minus a over b. So I can just try to solve for a over b, then put the negative sign, or I can just say, kind of with the practice and experience, you'll get used to it. That's why I mentioned reading the book is going to be different than the video. It's actually interesting here. So if you just say, let me leave this alone, what happens? The left side is going to be V0 or E naught there, or initial velocity over B, right? So in this general solution, we can replace that negative A over B with this new value or new quantity here. All right, and that's what's going on here. That's it. So now when you take that, you put it there, you get the solution to the initial value problem, right? So this is important to understand as we go into engineering and other fields. We found a general solution, right? We applied the initial condition, and it gave us what this negative a over b is. Then now we put it back in the general solution, and it gave us the solution to the initial value problem. All right. So that's very important to understand. Not that we have a new equation or something different or something brand new. We have a general solution to based on what was based on the assumptions that were given um, at the beginning, and then we applied a certain um, initial conditions saying that the initial velocity when t equals 0 is some v naught, whatever. We didn't say 0, we say some value, and it could be different things. Then using that gives you now a solution to the initial value problem, which represents now the velocity profile um, with including the initial velocity, the positive value for that resistance or air resistance. It accounts for the gravity and the mass and all that. So let's look at more details. Here we go. So what you should look at here, maybe a little bit hard to see when you look at this initial at this solution to this IVP is and try to understand it using the previous math. Look, you have a function or the dependent variable. T is the independent, and you have some constant here, the mass, the G, based on whatever we're looking at, to a certain degree to be constant and some initial velocity. So this is, remember, this is some value plus some coefficient or some value times e to some exponent. You know, the function e, for example, goes up or comes down, right? It has an asymptote. So if we try to figure out what is the asymptote here, it will be this mg over b. So whatever happened here, this will be driven to this value of mg over b. So just keep that in mind when we look at the profile. Then what else that's we need to kind of examine here? These two. You see, if V0 is greater than mg over b, it's not same as if V0 is less than mg over b. We know that from doing subtraction. 1 minus 2 is not same as 2 minus 1. So how these things will affect? When does V0, when does mg over b greater than V0? Think about it. If the mass is bigger, then this becomes bigger. If this air resistance is smaller, then this is going to be bigger again, right? So smaller, not even there, like vacuum or something, it's going to go fast. All right. If the mass is bigger, then it should drop fast. All right. So you can use some technology here. Because of time, I probably won't use, but I can show it in some other time or some other videos. You can easily kind of try to graph this profile here for the velocity. So let's show you here. All right, so you see that that's mg over b. Whatever happened, the velocity tries to go to that value. If V0 is less than mg over b, then it's going to speed up. Why it's going to speed up? Because in this cases, probably the mass is bigger or the resistance is smaller, and it's going to go try to speed up, go faster to it. And you can try some of these values. But what happens when V0 is greater than mg over b? Then it's gonna go to this, the velocity will be slower, right? It will kind of come down slower, just like if this is lighter or the air is thicker or something, right? So what we know if we do experiments, it's gonna match this profile, and this mg over b is called as limiting or terminal velocity. All right, I think I'll stop here. This is kind of just the idea of how to dissect a section. Thank you.